Hello, let's start our discussion with plasticity. What is plasticity? When a material is put under load, its shape changes or deformation occurs. If load is removed and material recovers its original shape, it is called elastic deformation. If shape is retained, then it is called plastic deformation. If load is increased and further increased, a maximum load will come at which material will fail or it will give yielding. So, plasticity is concerned with predicting the maximum load which can be applied to a body without causing excessive yielding. What is yield criteria? A yield criteria is a postulate, mathematical expression of the stress, states of stress that will cause yielding. And the most general form you can see here. For isotropic material, it can be expressed in terms of principal stresses, as you can see. There are many criteria, but only two of them are most accepted, and those are Tresca criterion and von Mises criterion. So let's talk about Tresca criterion. What is Tresca criterion? According to Tresca criterion, yielding will occur when the largest shear stress will reach a critical value, i.e. sigma 1 minus sigma 3 equals to C. C is some constant, means the critical value. If this largest shear stress reaches the critical value, then material will yield. This is the postulate of Tresca. This is Tresca criterion. And von Mises criterion says yielding will occur when RMS, root mean square of the shear stress, reaches a critical value. Effective stress. Effective stress is defined as a parameter which is a function of applied stresses which, when reaches a critical value, then yielding occurs. Here you can see the effective stresses for Tresca and von Mises yield criterion. Now, what is effective strain? Effective strain is defined as the incremental work per unit volume. Work means plastic work. And you can see the criterion effective stress in case of von Mises and Tresca criterion. The strain that results from elastic deformation are described by Hooke's law. You know Hooke's law? There are similar relations for plastic deformation called the flow rules. In the most general form, the flow rule may be written as this, where f is the function of sigma ij that describes yielding. For the von Mises, d epsilon 1 equals to d lambda into sigma 1 minus half of braces sigma 2 plus sigma 3. Similarly, d epsilon 2 and d epsilon 3, where d lambda equals to d epsilon effective strain upon effective stress, which varies with position on the sigma epsilon curve. However, d epsilon 1 ratio, d epsilon 2 ratio, d epsilon 3 remains constant. For Tresca, yielding function f equals to sigma 1 minus sigma 3, and so d epsilon 1 equals to d lambda, d epsilon 2 equals to 0, and d epsilon 3 equals to minus d lambda.
So our new topic is strain hardening. The first thing we need to know about the strain hardening is that it is one of the chief characteristics the plastic deformation possesses. It is a chief characteristic of the plastic deformation of metal that the shear stress required to produce the slip continuously increases with the increasing shear strain. This increase in the shear stress required to cause the slip because of the previous plastic deformation that has already been carried out is known as the strain hardening or work hardening. So the next thing we need to know about the strain hardening is what are its causes, meaning that what are really the factors behind this strain hardening thing. It is argued that it is caused by the dislocations interacting with each other and with the barriers which impede their motion through the crystal lattice. It means that you have dislocations that are the dislocations which were able to freely move earlier are not able to do this right now because there are dislocations which are obstructing their path. The earlier dislocation concept argues that the dislocation pile up on the slip planes at barriers in the crystals. These piles produce a back stress which opposes the applied stress on the slip plane. Thereby, we need to apply a larger force to cause the same deformation and therefore strain hardening occurs. The given figure indicates that the plot of resolved shear stress versus the resolved shear strain. As you can see in the figure given below, there are basically three stages. The stage 1 is the part in which the stress is increasing as you are increasing the strain. In the second region, in the second stage, the resolved shear stress increases very rapidly as you increase the strain. It can be further noted that the slope of the curve in the stage 2 it remains almost constant. The last stage, that is the stage 3, in this stage the resolved shear stress decreases as you increase the resolved shear strength. Let us discuss the three stages of the strain hardening in more details. The first stage, that is stage 1, is also known as the region of easy glide. It is the stage in which the crystal undergoes little strain hardening. During the region of easy glide, the dislocations are able to move over the relatively large distances without encountering barriers. And this is the reason why you see a curve with a very small slope, that is the stress is increasing very slowly in this region. The low strain hardening produced during this stage implies that most of the dislocation escape from the crystal at the surface. During the easy glide, slip always occurs only on one slip system. For this reason, the stage 1 slip is sometimes also called as laminar flow. So let us discuss now the stage 2 of the strain hardening. It is nearly a linear part of the flow curve where the strain hardening increases rapidly. In this stage, slip occurs on more than one set of planes. The length of the active slip lines decreases with the increasing strain, which is consistent with the formation of a great number of lower caudal barriers with increasing strain. These lower caudal barriers are the barriers to the movement of dislocations, which result in a high strain hardening coefficient. During this stage, the ratio of the strain hardening coefficient, that is the slope of this curve of the resolved shear stress versus resolved shear strain is nearly independent of stress and temperature and approximately independent of the crystal orientation and purity. The fact that the slope of the flow curve is in this state is nearly independent of the temperature agrees with the theory that assumes the chief strain hardening mechanism to be piled up group of dislocations. Let us now come to the stage 3. It is already evident by this stage that there is a sharp decrease in the shear stress required to cause the further deformation. What is the reason behind this decrease rate of strain hardening? The processes occurring during this stage are often called as dynamical recovery. In this region of the flow curve, the stresses are high enough so that the dislocations can take part in processes that are supposed and suppressed at lower stresses. Cross slip is believed to be the main process by which the dislocation piled up and obstacles during stage 2 can escape and reduce the internal strain field, thereby implying that the stress is being reduced. The stress at which the stage 3 begins is strongly temperature dependent. Also, the flow stress of a crystal strained into stage 3 is more temperature dependent than if it had been strained only into stage 2. This temperature dependency suggests that the intersection of forest of dislocations is the chief strain hardening mechanism in stage 3.
Let's start with the new topic, plastic instability. During tensile test, when the uniform elongation ceases, instability appears in the material in the local region. You have probably seen in the sample on which you have carried out tensile test. At the position of fracture, the local region is nagged. So let's understand this phenomena from the stress strain. Here you can see as you increase the applied stress, you reach the point of maximum load, which is called UTS, and it is the point where necking begins. There is a sharp decrease in cross-section area at the center of the sample. Let's now see the mathematical implication of plastic instability. As you can see from the previous curve, it will begin at strain where dP equal to 0, and we know P equal to sigma A, where sigma is applied stress and A is cross-section area. By differentiating from both sides, we get d sigma by sigma equal to minus dA by A, and we know as volume is conserved, so AL equal to A naught L naught, and further differentiating in both sides, we get dL by L naught equal to minus A naught dA by A square. And as from previous slide, L naught equal to LA by A naught, and by using elementary mathematics we get the result d sigma over d epsilon equal to sigma. Means necking occurs when slope of the true strain curve equal to true stress. Now starting with uniaxial case. With power law equation sigma equal to C epsilon power n, and by differentiating d sigma over d epsilon equal to n C epsilon power n minus 1, which gives the result epsilon equal to n. Similarly, for the case of balanced biaxial tension with sigma 1 equal to sigma 2, and using the procedure described earlier, we will get epsilon equal to 2n. And for the case of pressurized thin walled sphere epsilon equal to 2